Okay, so in this video we are going to learn about homomorphisms of groups and talk about when two groups are same. Okay, so let's start with this definition of a group homomorphism. So let G and G prime be two groups. So I'm going to write the definition and then we will discuss some examples. So let G and G prime be two groups. So this is the definition. A homomorphism of groups. So it is a homomorphism of groups. Is a function. So usually we denote this by phi. Okay, so this is read as phi. Phi is a function from G to G prime. It's a set theoretic function first of all. It's a function from G to G prime such that it satisfies the following condition. Phi of AB is equal to phi of A times phi of B. That's all. So we want phi of A B equals phi of A times phi of B. Okay, so let's just recall our convention here. When I write AB, remember this is for all. What are A and B? You have to ask. This is true for all A and B in G. So A and B are elements of the group G, the domain group, and in the bracket here I have A, B, which means A times B in the group G. I apply the binary operation of the group G to A and B. Phi of A and phi of B are elements of the group G prime, and here I write phi of A times phi of B, and that really means that I am applying the group operation of G prime. So the left hand side group operation is on of G is being used, and right hand side group operation of G prime is used. Okay, so let's keep this in mind. So it's not any set function but a set function which satisfies this. So a good way to remember this is to say this is a set function which satisfies or which respects the group operations of G and G prime. Whether you multiply first, so this is the way you should think of this. Whether you multiply first in the group G and then apply phi, or you apply phi first and then multiply in the group G prime, you get the same answer. This is what a group homomorphism is. Okay, so whether you multiply first and then apply G, or apply G f phi, sorry, multiply and then apply phi is same as apply phi and then multiply. So multiply and apply phi. Remember, when I use the word multiply, I really use it to stand for the binary operation of the group G. It's not multiplication of ordinary integers or rational numbers, right? Because G is an arbitrary abstract group. So multiply is just a convenient word to indicate the binary operation. So multiply and apply phi, that's what we have done in the left hand side, is same as apply phi and multiply. Which is what we have done on the right hand side. We applied phi first and then multiplied. So we started with A and B, we first multiplied them and then applied phi to get phi of AB. On the right hand side we have apply phi first to A and B separately and then multiply. So a group homomorphism is one where these two operations are going to give you the same answer. Okay, so let's start with some, after the definition, let's look at some basic examples, and before we continue study the properties of group homomorphisms. Okay, let's look at some examples. If you look at, okay, so let's look at this example. Let's look at our group that we have studied in detail, the group of integers. Again, when I write z, and do not say what the operation is, it's understood that the operation is addition. So for example, let's say I take an integer a and multiply by, so you fix an integer n, and I define phi of a to be n times a. So this is nothing but a plus a plus a n times. Is this a group homomorphism? Is this a group homomorphism? Let's check. So remember, what is it that we have to check? We have to check that if you apply the binary operation first, and then if you perform the binary operation and then apply phi, it should be same as applying the apply the function and then perform the binary operation. So in this example, it amounts to checking. We want to check a and b are two integers. You want to check that after adding them and then applying phi, or first applying phi and then adding. This should be true for all integers a and b, right? But in order to check this, let's just individually calculate them. What is phi of a plus b? By definition, phi of a is n times a, so phi of a plus b is simply n times a plus b. Phi of a is n a, and phi of this is actually b, right? Phi of a plus b should be phi of a plus phi of b, and phi of b is n b. So is n times a plus b equal to n a plus n b? Yes. So is this a group homomorphism? Yes. Okay. So this is a group homomorphism. So this is a good example of a group homomorphism, multiplying by a fixed integer n. Okay. Let's look at another example. So let's say I consider phi. So let's maybe I'll keep using the word letter phi for all these homomorphisms. Let's say I have 1 minus 1. I take this to be G prime. We have not seen this explicitly before, but is this a group? Is G prime a group? It is under our usual multiplication. Right, because 1 is the identity element, right, and minus 1 is the second element. Minus 1 squared is 1, minus 1 times 1 is minus 1, and so on. So this is really, G prime is actually a subgroup, if you think about it, of, let's say, rational numbers under multiplication. So I'll make that note here, and it's for you to check. Note that G prime is a subgroup of Q star. If you recall, Q star is the group of non-zero rational numbers under multiplication. So this is, G prime is just a subgroup of it. So I need to identify G prime as a group, right? In order to talk of group homomorphisms, we need two groups. We know that Z is a group, and now I am considering the group 1 minus 1. That's a group. So what is a map phi? So let's define the map phi. So define phi of A to B. So we have two cases. So let's define it to be 1 if A is even. So if A is even, I define phi of A to be 1, and let's say if A is odd, I define it to be minus 1. So phi of A is simply going to keep track of whether number A is odd or even. If it's even, we send it to 1. If it's odd, we send it to minus 1. So it's a function from the integers to the set 1 minus 1. Is this a group homomorphism? Is phi a group homomorphism? So again, remember one has to check that phi of A plus B should be equal to phi of A plus. Okay, so now this is a good example because it will make you deal with the notation that we have been using so far. If you go back and see the definition of a group homomorphism, I should say phi of AB equals phi of A times phi of B. But remember, I have clarified at that point that the multiplication here is whatever is a binary operation in the group that we are dealing with. So in this example, we have Z on the left hand side, which is a group under addition, and G prime, which is 1 comma minus 1, which is a group under multiplication. So in the definition, we have to check that phi of AB is phi of A times phi of B, right? This is what we have to check. But in this specific example, the left hand side is actually phi of A plus B, because the binary operation here is A plus B, the addition should be equal to, and what is the binary operation on the right hand side? It is just the multiplication. So it is phi of A times phi of B. Is this true for all A comma B in Z? Let's check this. Note that the image of phi is either 1 or minus 1 depending on whether A is even or odd. So let's take two even numbers. So let's say are both even. If they are both even, phi of A equals phi of B equals 1, because if both are even, they both go to 1. And note that then A plus B is also even. So phi of A plus B is also 1. If two even numbers are added to each other, we also get an even number. We again get an even number. So phi of A plus B is 1. And remember, then this condition is satisfied. So phi of A plus B is phi of A times phi of B, because this is 1 and this is 1 times 1. So this is okay. On the other hand, if A and B are both odd, then what do we have? Then phi of A and phi of B are both minus 1. But if A and B are both odd, what is A plus B? Sum of two odd numbers is even. So A plus B is even. Then what is phi of A plus B? That's 1. Again this condition is satisfied, right? Because phi of A plus B is 1. Phi of A times phi of B is minus 1 times minus 1. So this is again okay. So if both are odd, also phi of A plus B equals phi of A times phi of B, right? Now let's check the other case. So if A is even and B is odd, let's say in this case what happens? So we have phi of A is 1, phi of B is minus 1. Because A is even and B is odd, A plus B is odd, right? A is a multiple of 2, B is not a multiple of 2. So when you add, you won't get a multiple of 2. So A plus B is odd. So phi of A plus B is minus 1. Again, remember the function is odd numbers go to minus 1 and even numbers go to 1. So in this case again we have phi of A plus B is phi of A times phi of B, because this is minus 1 and this is 1 and this is minus 1. So this is okay. Okay, so similarly if A is odd, B is even, you can check that the same condition holds. So phi is a group homomorphism. Okay, so the function which sends an integer to 1 or minus 1 depending on whether it is even or odd is a group homomorphism. Okay, so the next obvious example would be to consider, so this is probably 3, is the function, the previous function modified slightly. So let's keep the same groups z and 1 minus 1, but now send A to minus 1 if A is even, 1 if A is odd. Okay, so I have interchanged the previous function. So here I sent even numbers to 1, odd numbers to -1. Now I am sending even numbers to -1, odd numbers to 1. Is phi a group homomorphism? Is phi a group homomorphism? I will leave this as an exercise for you. It's a very easy exercise. You can check that it is not a group homomorphism. You can produce two numbers which violate the definition of a group homomorphism. Okay, so this is an example of a function which is not a group homomorphism. So let me not do anything about this solution, because I would like you to try to do this on your own. One more example. Let's recall GLNR. So I don't know if I used the same notation before. Let me use this notation here, GLNR. So maybe I've used some other notation in the past, but the set GLNR, remember, stands for all invertible n by n real matrices. Under multiplication. Okay, so we take all invertible matrices which have size n by n and which have real entries, and I make it a group by multiplication, because now every matrix in this set has an inverse because it's invertible. Product of two invertible matrices is invertible, and inverses exist by definition, and so on. The multiplication of matrices is associative, identity is there, so it's a group. This is a group under multiplication. Now we all know what determinants of functions are. So I consider the determinant function. So let's take phi from GLNR to non-zero real number. So I take a matrix A and I define phi of A to be determinant of A. So which is simply written dit A. So dit A is the function which sends A to determinant of A. This is a function. So is phi a group homomorphism? Now, first of all, before you even attempt to answer this question, you have to ask yourself, what are the two groups involved? I just recalled for you what is GLNR. Okay, GLNR is the group of all invertible n by n real matrices under multiplication. But what is R star? R star is all non-zero real numbers also under multiplication, right? So this is also a group that we have seen before. If you take non-zero real numbers and consider the binary operation given by multiplication, it's a group. So now I can ask, is phi a group homomorphism? It's a function from one group to another group, and the answer is yes. And it follows from the properties. If you have seen matrices before, properties of the determinant. What do we have to check? We have to check again. Remember, the definition of a group homomorphism is phi of AB should be same as phi of A times phi of B. I'm going to use letters capital A, capital B, because that's more standard to denote matrices by capital A, capital B. Remember, again, I recall for you, the definition of a group homomorphism is phi of AB must equal phi of A times phi of B. So is this true? Yes, because what is phi of AB? This is determinant of AB. And what is phi of A times phi of B? This is determinant of A times determinant of B. And if you have studied matrix theory before, and when you studied determinants, one of the first properties that you will see is that det A B is equal to determinant of A times determinant of B. This is a property of determinant. So this is a well known property of determinants. So because this is a well known property of determinants, phi is a group homomorphism. So this is an important example of a group homomorphism. So let's look at one more example. So 5 in my counting. So let's say G is an arbitrary group. So I am going to take any group and fix an element A in G. Fix an element A in G. Consider the following function from the group of integers to G, which sends phi of A to phi of now because I have used A for the group element, let me use n for the integer. Phi of n to be, I define it to be A power n. Remember again, A power n stands for A star A n times. So I am applying the binary operation of our group G to A n times. So this is phi of n equals A power n. Now is this a group homomorphism? So again, remember the definition is phi of m plus n. Because the group Z is under addition, we have to check phi of m plus n should be equal to phi of m times phi of n, because that's the group operation on G. My notation is just phi m times phi n. So I don't write star unless I want to emphasize a point here. So is this true? But what is phi of m plus n? This is A power m plus n. By definition of phi, m plus n goes to A power m plus n. This is true. And what is phi of m times phi of n? This is A power m times A power n. Okay. So now the question is this true? Is A power m plus n equal to A power n dot A power n? And the answer is yes, this is true. And this came up in some of the work that we have done in the past when we worked out some examples or looked at some properties of multiplication. So I am not going to spend a lot of time doing this, but quickly I will do this. What is this? This is A star A m plus n times. And this is, first I will do A star A m times, and then I do star. Note that I am using dot and star interchangeably here. In the second we have n times. Okay, so we have A star A m plus n times, and here m times and then star n times. But this is if you use associativity of group operation and expand this out, you have to do first A here, and then so you take this and do this A power n. So this is, remember, A power n. So this is A power n plus, or rather I should use, I am using the distributive property, the associative property. So then you have another A star A power n, like that, and this is m times. So this is A n plus 1 star A n plus 1 star n plus 1. So if you keep doing this one by one, you get A power m plus n. Okay, so this is an exercise for you to check this. So check this as an exercise. Okay, so I remarked this on this earlier. When I use the exponential notation, I can use the usual properties of exponents that you have studied about real numbers and integers and rational numbers. So this will go through. Okay, so this is a group homomorphism. So let us do one more example. and then we'll study some properties. Now fix again a group, but assume now that it is abelian. So what is an abelian group? Recall, G is abelian if AB equals BA for all AB in G. Okay, so any two elements in G commute with each other. So this is an abelian group. Okay, so now I consider the map free from G to G, which sends A to A squared. Okay, so what am I doing? I am taking an element A and I am simply squaring it. Is this a group homomorphism? Is this a group homomorphism? So we have to check, remember, check phi of A B should equal phi of A times phi of B. Let's just write both sides of this equation. What is phi of AB? This is AB squared, right? That is the definition. Send any element to its squared. And what is this? This is A squared times B squared. Phi of AB is AB whole squared. Phi of A times phi of B is A squared times B squared. Now are these two equal? And here is where we have to use the abelian hypothesis. So let's just write it down. So AB whole squared is AB, AB, right? This is the definition of AB whole squared, AB, then AB. Because the group is associative, so I am going to just remove the brackets and write this as AB, AB. What is A squared, B squared? This is AA, because that's what A squared is, times BB. So again I will remove bracket. So this is AA, BB. See, there is no reason in general that these two are equal. In general, these are not equal. But note that we are in an abelian group. I'm starting with an abelian group. So AA, BB I can interchange in any way I want. So I can interchange the middle two elements, that is AB, AB. So if I interchange this, because AB equals BA, I have noted that AB equals BA for all AB, AB equals BA, so this is AB times AB. So this is true. So the map which sends A to A squared is a group homomorphism if the group is abelian. So now the question naturally arises, is phi a group homomorphism when G is not abelian? Okay, so is this a group homomorphism when G is not abelian? Note that our proof here suggests that it need not be, right, because in general we may not be able to interchange A and B here. But unless we get an example, we can't be sure. Just because the proof that we are trying to give here does not work in the non-abelian case, the statement itself is wrong for non-abelian case, you cannot say that. Maybe there is some other proof. Okay, so unless you give an example where this is not a group homomorphism when G is not abelian, you can't conclusively settle this question. So in order to understand this, think of the groups that you know that are not abelian. The simplest such group is S3. So consider, remember that in an exercise in an earlier video we have shown that any group of order up to 5 is abelian. So 1, 2, 3, 4, 5 is abelian, and hence G3 S3 which has 6 elements is the smallest non-abelian group. And in the notation that I introduced way back in one of the first videos, I use these letters to denote the elements here. These are all bijections of the set 1, 2, 3 to itself. S3 is always the set of bijections from 1 to 3 to 1 to 3. So now consider the map from S3 to S3. I map Fi, phi sends Fi to Fi squared for every I from 1 to 6, right? So F1 goes to F1 squared, F2 goes to F2 squared, and so on. So now I want you to check as an exercise here, and this is a straightforward exercise. It's a good way to again remind yourselves about the group operation of S3. Phi is not a group homomorphism. Okay, so you can check that phi is not a group homomorphism. For example, maybe I'll just quickly tell you how to check this. If you recall F2, so I will recall for you from the first video, F2 sends 1 to 2, 2 to 1, 3 to 3, and F3 sends 1 to 3, 2 to 2, 3 to 1. So where does F2, F3 go? So let's do this. If you multiply F2 and F3, 1 goes to, so first you send 1 to 3, then 3 to 3. So 1 goes to 3, 2 goes to 2, and then 2 goes to 1, 3 goes to 1, and 1 goes to 2. So is this clear? So F2 was this, F3 was this, and F2, F3 is this. And this, if you recall again the notation that I developed in the video where I discussed this in detail, this is same as 1 goes to 3, 2 goes to 1, 3 goes to 2. So in the notation is F6. Okay, so F2, F3 is F6. So now if this is a group homomorphism, we want, and where does F2 go under phi? Now this is F2 squared. We checked that F2 is actually an order 2 element in when we discussed orders of elements of a group. So F2 squared is F1. Similarly, F3 is also an order 2 element. So phi of F3 is F3 squared, and that's 1, namely F1, the identity element. Okay. On the other, so in other words, phi of F2 times F3 is phi of F2, F3 is f of 6. Phi of F6 is F6 squared, and F6 is an order 3 element of S3. So this is not F1. On the other hand, phi of F2 times phi of F3 is F1 times F1, which is F1. Okay, so phi of F2, F3 is not equal to phi of F2, phi of F3. Okay, so I have actually checked all the details here. You have a non-abelian group where the multiplication squaring is not a group homomorphism. So this exercise is completely checked. However, if the group is abelian, you have that it's a group homomorphism. Okay, so I'll stop the video now, this video. In the next video, we are going to study some basic properties of group homomorphisms and learn more about subgroups attached to group homomorphisms. Thank you.